Recording, there we go. Okay. All right, so the plan is this. We have Tuesday, as you all know, Thursdays, we're going to make them study days. So Thursdays till the end of the semester, that's a good time to come in if you have any questions. And Tuesdays, today, we're going to go about halfway to chapter 14. And then the next Tuesday, we will finish up chapter 14. And then the following Tuesday will be chapter 15, which is like a very short chapter. And then that will give you plenty of time, hopefully, to prepare for exam, the last one, which is the following Tuesday. Okay. And so we have a multiple of days that we have for you to use to help you out with questions and so forth. Now, you're more than welcome to come to my 1 o'clock also. Same schedule. So feel free to do that. And I also have they're like one chapter behind, but my Friday at SEC class, and that's from 1 to 3. You're more than welcome to come to that also. No problem. They're like one chapter behind. So I'll be doing, I think, starting chapter 13 with them. Okay, so use those days that we have if you need assistance. If these days don't work, send me an email. We'll see what we can do as far as setting up a Zoom time, because I do have time between the 1 o'clock class and your class. So roughly between 2:30 to 3:30. So we can use those days, those hours, if you need some help with something. Let's see what else. So that's the plan. So we're getting close to the end. On the website, there is a final exam practice, a practice final exam. I would download it, use that as a resource. Final exam is very similar to the exams you've been doing so far. It is comprehensive, which covers all the chapters. So start thinking about that. And then don't forget, I do have a extra credit. It is in the section with the final exam. At this point, I believe it's 15 points, so it could be a big help. So basically, download the file, follow the instructions on the file, save your data in the digital file, rename your file, upload it back into the assignment, and then you're good to go. Okay? All right, so let us start with, excuse me, 14. Okay. Now, throughout the semester, I've always stated, hey, we're doing this particular chapter because we're going to use it down the road. Well, we're here. Okay. Because we have gone through in the past drawing Lewis dot structures. This is a good place again to refresh your memory on that. We talked about polar bonds, okay, and nonpolar bonds for covalent compounds. We also talked about whether the compound will be the molecule itself, even though the bonds are polar. How does the polarity of the bonds of the molecule affect the overall polarity of the compound or the molecule that you're working with? Okay, because all of that comes to fruit here, because we're going to tap in the fact about electronegativity and having polar bonds and the polarity of the compound and so forth, and put it all together here, because we're talking about what are called intermolecular forces. These are the things that interact, these are the forces that affect the properties of the chemicals that we utilize every day, actually. For example, I may have mentioned this, but I'll do it again. If we take a cup of honey and we take a cup of water and we play the race as far as emptying those two cups, obviously, you know who's going to win the race, right? The water is. Well, we know that the water is going to win the race because the honey is a lot more viscous. Well, it's a lot more viscous because of the forces of the honey molecules have with each other. And some of these forces are pretty strong, some of them are pretty weak. These forces are called intermolecular forces. The prefix INTER, that deals with interactions with other molecules outside itself. Now, we have been dealing with intra forces, INTRA, and that is dealing with the bonds within the molecule, be it ionic bonds, be it covalent bonds, and if there were covalent bonds, be it polar or nonpolar covalent bonds, okay? And so these forces come into play together, not only the inter, but the intra forces. Okay, so if we, for example, take a look at this two diatomic molecules sitting here, what we're talking about is this dotted line, okay? This dotted line represents the interaction of this looks like a diatomic species with another diatomic species in itself, okay? These are the intermolecular forces that occur compared to the intra, which deals with the force of keeping the atoms together, which is the chemical bond, okay? And of the two, the IMF forces compared to chemical bonds are much weaker than chemical bonds. They are much weaker, but they have a big effect on the properties. For example, we know that water boils at 100 degrees Celsius, okay? Whereas, let's say, ethanol or drinking alcohol boils at I believe, 78 degrees Celsius. That's a wide range, okay? And we also know that acetone, otherwise known as, you may know it as a nail polish remover, okay, acetone, it's very volatile. You open a container up and the stuff, you can smell it because it's very volatile. You put a little bit on the cup or a container on a bench top, it evaporates quickly. But when we look at the intermolecular forces between water, ethanol, and acetone, those forces for acetone are very weak with each other. Molecules of acetone don't interact as strongly as the molecules of water interact because water takes 100 degrees of temperature to get it to boil, temperature and energy to get it to boil. That's a lot. Ethanol, 7 degrees. So that infers that the intermolecular forces of water and ethanol, those forces are much weaker. Otherwise, their boiling point would be much higher. And it's all related to these crazy electrons that I've been talking about all semester. Electrons have a big, big factor. Okay, so let's as I mentioned up there, when the intramolecular forces, we're talking about the bond in the atoms. Inter, we're talking about the interaction between molecules of whatever we're looking at. In this case here, we have hydrochloric acid, okay? And that blue dashed line represents the IMF interaction between the two. Okay, now there are four types of forces. You would think there would be a lot more, but they're not, okay? The first type is called London dispersion forces. London dispersion forces. So any nonpolar compound molecule, any nonpolar molecule, the only force they have, and the only intermolecular force they have are the London dispersion forces. So what does that mean? You got to go refresh your memory about how do I define what is a nonpolar molecule, okay? And we'll have more to say on that, but go refresh your memory on that. Type number 2 is what we call dipole forces. Dipole forces. So that means that any polar molecule, this is true for any polar molecule. Their force, intermolecular force, is the dipole-dipole. Okay, we'll have more to say about that here in a bit. Again, being a polar molecule, refresh your memory. How do I know something is polar? Okay, we'll come back to that also in a bit. Third type, okay, we call that hydrogen bridging forces, HBF. Now, these are dipolar molecules, dipolar covalent molecules, but these deal only, and I repeat, only with hydrogens bonded to nitrogen. So I write in here a bond between hydrogen and nitrogen, or hydrogen bonded to oxygen, or hydrogen bonded to fluoride. Yes, they are dipole. Okay, I just say D-D. Yes, they are dipole. But because of the fact that you have a hydrogen bonded to a nitrogen or an oxygen or a fluoride, there's a different forces then is stronger than a dipole. And so that hydrogen force truncates the dipole. It is stronger. Okay, I repeat that. Even number 3 has a dipole interaction. The fact that hydrogen is bonded to nitrogen, oxygen, and fluoride, the hydrogen bridging force takes preference. Okay. And then the fourth one is called the Ion-Dipole Force. Well, here's the thing on this. Ion, okay? The term ion suggests an ionic compound, obviously. So all ionic compounds that we have out there are involved with this ion-dipole interaction. So we have an ionic material, so things like sodium or all the ions, sodium, all the metal ions, all the chloride ions. But the dipole refers that there's another molecule involved here that has a dipole interaction. But since we're dealing with ionic compounds, the only possible molecule that has a dipole interaction is water. So we are dealing with aqueous, or H2O, mostly water. So an aqueous system. So when you have an aqueous system and an ionic compound dissolved in there, be it soluble or insoluble, remember even insolubles have some ions in solution, not as much as something that's soluble, but still there, okay? And so that infers that we're only dealing with ionic compounds and water, aqueous systems. Has no relationship with 1, 2, and 3, okay? Because 1, 2, and 3 deal with covalent compounds. Okay, 1, 2, and 3 deal with covalent compounds. Whereas 4 deals with ionic and an aqueous system. All right, so let's go back. Refresh your memory on polar, nonpolar. Remember, we have 2 types of compounds. We have ionic compounds and covalent compounds. Or go back further, we have ionic bonds and covalent bonds. Ionic bonds require, by definition, are defined as those compounds that have a metal and a nonmetal. Okay, so any metal and nonmetal connection, partnership, if you will, are ionic compounds. That's important. Some people are still having trouble with that concept. But I don't know what other way to put it. I got a metal and a nonmetal. Think of sodium chloride table salt. Sodium is a metal, chloride is a nonmetal. Covalent compounds deal with 2 or more different nonmetals. Okay, nonmetals. So H2O, water, hydrogen, and oxygen, both nonmetals. So covalent compounds deal with 2 or more nonmetals. Now we have a subcategory of the covalent compounds. When there is equal sharing in that bond, now let me retract for a second. In ionic compounds, ionic bonds, they're not really a true bond, but they're classified a bond. If you name it a bond, it is more like magnets coming together because the ionic compounds have a full-fledged positive, full-fledged negative. They come together and attract to each other like magnets. You call it electrostatic attraction, okay? Covalent compounds, nothing like that. There's actual a sharing of the bond. The non-polar compounds or covalent bonds, the 2 atoms are the same, okay? Same elements or carbon-hydrogen. So all the diatomic and the carbon-hydrogen bonds are non-polar bonds. Equal sharing. The polar bonds, there is unequal sharing. And the reason there's unequal sharing because for polar bonds, there are 2 different atoms. There's another concept sometimes people are not getting. For a covalent bond with 2 different atoms, automatically polar bond except carbon-hydrogen, okay? Again, I repeat, for a covalent bond, 2 different atoms, polar bond except carbon-hydrogen. Now, there's unshared sharing, unequal sharing of that bond because now we refer back to EN, electronegativity. Electronegativity was a measure of how, the measure of the affinity of the bond of the electrons toward itself. And we use fluorine as our reference point on the periodic table because fluorine is the most electronegative element on the periodic table. And the trend was left to right, top to bottom, the electronegativity increased. So if we needed to compare the electronegativity of 2 atoms that are bonded, like carbon and nitrogen bond, we look at their position on the periodic table relative to fluorine. So if we look at carbon and nitrogen, nitrogen is closer to fluorine. Therefore, fluorine has a higher electronegativity. Therefore, the electron density is pulled onto nitrogen more so than the carbon. Therefore, we create a partial negative onto the nitrogen and a partial positive onto the carbon, okay? Therefore, when we draw the dipole arrow, the point is pointed toward the nitrogen and the tail is toward the carbon, okay? And that is a polar molecule, polar bond. Now, with respect to molecules, how do we know if the molecule is polar or nonpolar? Well, for nonpolar compounds, when you have all nonpolar bonds in a molecule, okay, you have a nonpolar molecule, plain and simple. Okay, if it's diatomic, they're both the same element, the same atom, so there's no there's equal sharing of that bond, so it's nonpolar. Okay, now with respect to polar molecules, in general, when you have all polar bonds, you have a polar molecule, unless the polar bonds cancel each other out, okay? I repeat, for polar molecules, you generally have all polar bonds unless the polar bonds cancel each other out. Now, if you recall, how do we know if they cancel each other out? Well, this is where we went with the Lewis dot structures. At one point, we did work with carbon dioxide, and we used the Lewis dot structure procedure to find its structure. And we came up with this oxygen double bonded to carbon, double bonded to oxygen. Okay. Remember how we did that? We got all the Lewis dot structures. Remember the octet grew, and we put all the electrons all the way around all the elements, and then we looked for the octet. If we were shy someplace with respect to octet, we borrowed the electrons to make double bonds. Carbon dioxide was one of them. Okay. Now, carbon, oxygen, that is a polar bond. Two different atoms. Okay, plain and simple. Two different atoms, I got a polar bond in both directions. But we'll get more in that. This is just a refresher. Now, which direction is it happening? Which direction is the polarity? We look at the electronegativity of oxygen and carbon relative to fluorine on the periodic table. Oxygen is closer to fluorine. Therefore, the electrons are pulled more toward oxygen than carbon. The result is that we have a dipole going in the direction of the oxygen. And that gives us our partial negative on the oxygen, which gives us a partial positive on the carbon. Now, on the other side, we have the same scenario, but it's going in opposite direction. Okay? Now, I was asked a question, what do you mean they cancel out? Well, I'm going to add a little side note of information that really we didn't cover. I may have touched on it, but this may explain why those arrows cancel out. Those arrows represent what we call what are called vectors. Okay, it's something we use in mathematics, but that's okay. We're not going to get into that. Basically, it's tell you that a vector has direction and magnitude. In other words, if I say to you 20 miles, that doesn't mean anything unless I tell you 20 miles north. That's a vector because I'm giving you magnitude and direction. That arrow represents magnitude and direction. The arrow on the right, both arrows, though they're a little bit not together in size, they should be written with the same size because I got a carbon, oxygen on one side, carbon, oxygen on the other side. The magnitude is the same. The difference is the one on the right, like any mathematics, we have an axis with the zero in the middle. The one on the right is going in the positive direction, so it has a positive magnitude. The one on the left, relative to carbon, which carbon is a 0 point, is going to the left or in the negative direction, okay? That means that the one on the left in negative magnitude cancels out the one on the right in positive. So those arrows represent, you can simply just visually see that they go in opposite direction and they cancel each other out. If they were going in the same direction, they would be cumulative. And they both had 10 units, it would be 20 units if they're going the same direction. But they cancel each other out. So in these examples, you have polar bonds that cancel each other out, resulting in a nonpolar molecule, okay? The tetrahedral configuration. If you have polar bonds in the tetrahedral configuration, much like, say, carbon tetrachloride. Okay, you have four carbon in the center, four chlorides around it. They go back to your shapes table, you refresh your memory, they'll be tetrahedral. Those bonds are equally spaced as much as possible away from each other. Okay, there are four polar bonds in that compound. However, in the tetrahedral configuration, those four polar bonds cancel out. Therefore, carbon tetrachloride will be nonpolar, even though it has four polar bonds. The fact that it's a tetrahedral, they cancel out evenly. Hence, I have a nonpolar bond. The moment I replace one of those with, say, I don't know, bromide, now those four polar bonds do not cancel out because I got one of them with a different magnitude. Okay, so then I end up with a polar species. So go back and refresh your memory about polarity, polar bonds, polarity. and so forth, okay? Because we will use it here. All right, let me on. Now, dispersion forces. These are temporary forces here. Now, temporary in that electrons actually get pushed to one side to create a temporary dipole. Polar bonds are permanently a dipole. They have a permanent partial positive and a permanent partial negative. Okay, just like a battery, plus a permanent positive and a permanent negative side. Okay, all polar bonds have that, a permanent dipole. Non-polar bonds have a temporary dipole, and that happens because of these electrons. Okay, let me explain how. Have you ever taken a balloon and rubbed it on your head, and then take that balloon and let it stick to your chest? How did that happen? How does that happen? How does that happen that you get that balloon to rubbed on your head or someone else's head, and then you stick that balloon onto your chest? What's making it stick? Some Harry Potter magic?
Correct.
Was it the Harry Potter magic? Okay. Yes, Harry Potter magic called the electrons. Okay. Think about this. Your hair is I told you before, the electrons are all around us. We're just inundated with electrons. You walk on a carpet, especially a brand new carpet, you walk in it for a little bit, touch something, what happens? Zap. You're in the shopping cart pushing some cart, so you're pushing it and you touch something, you get zap. People call it electrostatic charge, okay? You wake up in the morning, your hair is doing this, poof, right? Bad hair day. That's because your hair is loaded with electrons. Or you put on a pair of pants or a dress that clings to your clothes, clings to you, and you have to put an anti-static spray on that, which alcohol, by the way, works real great for that. It's these crazy electrons. Now, as you take that balloon and you rub it on your head, you're literally transferring electrons to the surface of that balloon. So that balloon now is supercharged with electrons. As you bring it to your chest, well, on the surface of your chest, you have electrons. There are electrons from your shirt, okay? They're out there. Like I said before, we never ever touch something literally, because when we grab something, all we're doing is holding on to electrons when we grab anything. And so as you bring that balloon full of electrons onto your chest, remember, electrons are negative charge. The electrons on the balloon are negative charge. The electrons on your chest are negative charge. And so the ones in your chest, some of the balloon get pushed away, creating a temporary positive side on your chest. Okay, a temporary partial positive, because you push the electron density away from the surface, and you got a partial negative on the balloon, hence it sticks. Now we all know that doesn't stick there forever, and it's not that strong, but it sticks. Okay, because you have created a temporary dipole. Okay, and this is what happens with nonpolar molecules. There are interactions. Remember, there's electrons all around it. And just by coming close together, electrons get pushed around and get pushed apart from each other, creating a temporary dipole, which we denote, this interaction right there in red. Okay. Now, those are very weak. So London forces are pretty weak interactions. But London forces, the only thing, the only force, intermolecular force, that nonpolar molecules deal with each other are London forces. Now, the other thing I asked was back here, the last thing. The bigger the molecules, the more electrons, the more London force involved. So ever wondered why vegetable oil is liquid and lard is solid? They're both made up of basically carbon and hydrogen, hydrocarbonate. They're nonpolar species. Okay. But any idea why vegetable oil will be liquid at room temperature and lard, aka manteca, is a solid, or for that matter, butter is being a solid. And they're all essentially made up of carbon and hydrogen, just long chains. Okay, well, as this states here, the bigger the molecule, the more electrons that there are, the more London forces that occur, the more the effect is on the overall property. And so when I look at vegetable oil, which is a liquid, and solid lard, which is a solid, they both have London forces involved, but the lard molecules are bigger. There's more electrons. There's more interactions that hold more London forces interactions that hold the molecules closer together. Hence, you have a solid material at room temperature. Now, think about it. If I take that solid lard and I put it in a hot pan, what happens to it? What happens to it? What happens to that stick of butter and I stick it in the pan that's warmed up?
It melts.
It melts, exactly, because what you're doing is you're breaking up that interaction that the arrow is showing you. You're breaking up that interaction, just like having a senior moment here. The honey. How do I make that honey flow as fast as water? I heat it up. If I heat it up, it becomes more liquidy, and the reason it's become more liquidy, I'm breaking up those interactions between the molecules. I'm breaking up the intermolecular forces. Okay, some of these forces are pretty strong. Water boils at 100 degrees, so the intermolecular forces to keep the water molecules together is pretty strong. I got to bring that temperature pretty high to get them to break apart away from being a liquid and go into the vapor phase. Let me see here. Let me clear this. All right. So that's for London forces or nonpolar molecules. They're there because they temporarily make a dipole. Now, for those that have a permanent dipole by virtue of the two atoms that are bonded, okay, we have the example here of hydrochloric acid. All right. We have a dipole that goes from the hydrogen to the chloride. And we denote that again by the dipole arrow going in the direction of the chloride in both cases. Okay. Well, it has created a partial negative side and a partial positive side. Opposites attract, so they're going to get together and have an interaction occurring right in here, denoted by that dotted line. Okay. That is the intermolecular force between the molecules. And that occurs. Now we show a two-dimensional picture here, but nature is three-dimensional. So this is all happening all around us, X, Y, and Z axis, not just the X and Y. So these forces are interplaying all around. Okay, so that is a dipole-dipole interaction or dipole forces. Yeah. Okay. Thing about the strength. London forces are the weakest. Okay. Then comes the dipole-dipole forces. But in order to have dipole forces, you must be a polar molecule. Okay. It must be a polar molecule, which obviously you got to have polar bonds that do not cancel out. Now, hydrogen bridging. Now, the old textbooks, you may see the term bonding used, and much like ionic bonds, the hydrogen bridging is not a true bond. It's an interaction. And so the name bridging is trying to be, they're trying to use that, which is more indicative of what's really happening as compared to using the term bonding. But I put that in parentheses because you will find some literature that still use hydrogen bonding as the term. So we can see with water here that we have a partial positive and a partial negative. In fact, oxygen has two partial negatives because it has two polar bonds, not to mention the lone pair sitting on the oxygen. And so it will form a very strong interaction right there, much stronger than the dipole-dipole, but only when the hydrogen is bonded to nitrogen, oxygen, and fluorine, okay? Yes, water, in this example, anything that has any of the three there, yes, that is a dipole, okay? Water is a dipole. However, because it's hydrogen bonded to oxygen, it has an added strength to it, which is called the hydrogen bridging force. And it is much stronger than the dipole-dipole. Okay, so don't forget NOF. I also call it not on file to help you out. So that's hydrogen, that's important. Hydrogen bonded to either nitrogen or oxygen or fluoride. Okay, you can see the picture here on the right. It is a three-dimensional picture of the water molecules, how it's happening all around it. Very strong interaction. So when we put energy into the system, we're breaking up that interaction there. Okay, and it takes a lot of energy to break up that interaction. All right, so hydrogen bridging, when it comes to strength, the weakest is London dispersion forces, then comes dipole-dipole, and then we got hydrogen bridging force. Those are the three covalent forces, intermolecular forces that we deal with, okay? Not to be mistaken with the bond forces, which are much, much, much stronger than these forces here. Now, with respect to the ion-dipole forces, as I mentioned, we're talking about an aqueous system, okay? So we got water involved. And here we have an ion with a full-fledged negative. So we have a picture of a model of the sodium ion with a full-fledged negative being stabilized, if you will, or hydrated with the water molecules around it. And it's hydrated or stabilized with the oxygens of the water molecule because remember, the oxygens have two partial negative sides to it. And so the water molecules extremely surround the ion. Now, picture, if you will, on the other side with the protons, if this were sodium chloride, that we would have the chloride, let's see if I can draw it, the chloride on the other side, okay? Next to the, that's supposed to be Cl, next to the C, yeah. So interacting with the partial positive of the water molecules. This whole matrix, pretty ordered matrix, is what stabilizes the ions in solution. Okay. Now, remember when we talk about ion-dipole forces, we are talking about an ion, be it a soluble or insoluble ion, and the dipole part comes from the water molecule. Okay. So let me summarize some of this stuff, and what I'm going to do, I'm going to stop it in this slide here. Okay. But the bonds, when we talk about, I think I'll go one more slide. When we talk about bonds, we got ionic bonds. Okay. We're talking about a metal and a non-metal ion together. And it's electrostatic attraction, like two magnets. When we talk about covalent bonds, we're actually sharing electrons between atoms. And covalent bonds are two categories of covalent bonds, either polar or nonpolar. The polar covalent bonds due to unequal sharing because one of the atoms has a higher electronegativity and therefore is pulling the electrons away from the other atom. And nonpolar, we're getting an equal sharing of electrons, okay, because most of the time they're just two of the same atoms or carbon hydrogen. That's the bonds. Now, with respect to the forces, we got four forces. London forces that only nonpolar molecules have. And then we have dipole-dipole force, which only polar molecules have. And then we have hydrogen bridging force, which, yes, polar molecules have, but only those that have a hydrogen and nitrogen or oxygen or fluoride bonded to it, okay? And then we have the Ion-Dipole Force, which deals with an ion. And most of the time, 99.9% of the time, the dipole force comes from the water. So that's basically the water solvating the ion. Okay. The first three deal with covalent compounds. The weaker one is a London, followed by the dipole, and then the stronger one is a hydrogen bridging force. We're going to utilize that force to determine such properties as boiling point, things like vapor pressure, things like surface tension, okay? Those kind of properties we're going to be able to determine when we compare two different compounds. Now, we're not going to be able to give absolute values, but we'll be able to predict, one, for example, who's going to have a higher boiling point. For example, like I mentioned earlier, water boils at 100 degrees, ethanol boils at 78 degrees. So that infers that water has stronger IMF interactions, okay? Much stronger IMF interactions. In fact, ethanol and water both deal with hydrogen bridging forces, but water being having two dipoles has much stronger hydrogen bridging forces. Okay, so let me stop it after this, and we'll go from there. So here in this example, in this table, what they're asking you first to determine the molecule given whether it's polar or nonpolar. Then from that information, write down or determine which is the strongest intermolecular force for that molecule. Okay. Now we had carbon dioxide. I showed the diagram earlier for the structure for carbon dioxide. Had two polar bonds, but they cancel each other out. Therefore, carbon dioxide was nonpolar. So here, recall that chapter where we had the Lewis dot structures. We have to figure out the structure. We use the shapes table to figure out what shape it is and so forth. From that information, we're able to determine whether the molecule is polar or not. So you may go back and refresh your memory on that. So carbon dioxide is nonpolar because the dipole bonds cancel each other out. Being nonpolar, the only force it deals with are the London dispersion forces. Okay. Now, phosphorus trifluoride. If you look at phosphorus, which is a central atom, it's in group 5. And back when we were dealing with structures, I said, well, group 5 atoms, nitrogen and phosphorus, the neutral species, when they only will have 3 things bonded around it, and you will end up with a lone pair on the central atom. And whenever you have a lone pair on the central atom, guess what? You got a polar compound, okay? Now, you would think, once you come up with this, you have a lone pair, you might think, I got a lone pair and 3 fluorides bonding around fluorine, around phosphorus, that would have tetrahedral, and which means that everything cancels out because the phosphorus fluoride bond is polar. But remember, the lone pairs take up a lot more space. And so they would cause that bond angle, remember the bond angle, to be much smaller than 109.5. And so that species would be polar, regardless of what's bonded, whether they have polar bonds or not. It's polar. So polar bond. And then how do we determine? Well, first of all, it's not London force, so we can eliminate that. It's not ion-dipole because there's no ions mentioned here, so we can eliminate two of them. So that leaves us with either dipole-dipole or hydrogen bridging. Well, it can't be hydrogen bridging because there's no hydrogen involved in PF3. Okay, so the obvious choice left by process of elimination is the dipole-dipole. Okay, I'm going through each one because like what I've done in the past is kind of go through a systematic approach of getting to your answer until such time that you can look at it and don't have to do that. But this helps you out to figure out, okay, which one am I going to use? All right, the next one. Point number one, you got hydrogen there. It's an acid. Point number two, it's a fluoride. So it's definitely a polar bond. Okay. Second of all, being polar and I got fluoride, I got hydrogen, automatically to send you to hydrogen bridging. Because remember, not on file, hydrogen bonded to nitrogen, oxygen, or fluoride. Okay, so we got a polar species. So this is hydrogen bridging. Yes, there's a dipole. There's no question about that. But it is hydrogen bonded to fluoride, which adds an additional force to it, which is much stronger than simply the dipole-dipole. Okay, the next one. Yeah, carbon and hydrogen. That is all you see in the formula. One carbon for hydrogen. It could be 10,000 carbons and 10 billion hydrogens. The fact that you see nothing but carbon and hydrogen should tell you hydrocarbon. Okay. Not only that, it should tell you nonpolar, because it's all made up of nothing but carbon hydrogen bonds. All nonpolar bonds give me a nonpolar species. Therefore, the only force I would have to deal with would be London forces. Okay. Next one, you have Ki, and you got AQ. AQ means it's an aqueous solution. You got K, which is potassium, which is a metal. Okay, and I, which is iodide, which is a nonmetal. So you have an ionic compound. So the only obvious choice, none of the other three choices would be a factor: London, dipole, hydrogen bridging, because all those are covalent compounds. Ki is not covalent. And so this is ionic in this case, polar water, okay, which is the Ion-Dipole Force. All right, so let me stop it here. Keep you in line with the other classes here. So what we'll plan, here, let me stop. Somebody has a question. Okay, there you go. If you got a bad hair day, you can blame it on the electrons. I just saw your message, Brian, which is true. It's not, you can have a bad hair day due to if you look at what they put on the hair material. Let me see. Is there something here?